All right, ladies and gentlemen, today we will be starting the Unit 6 Thermochemistry. This is Chapter 5 in the Brown-LeMay book. We have covered a lot of different things, and now we are going to dive deeper into what the chemical reactions are going to give us. First thing we will need to discuss is some things about what is a system and what is the surroundings. Because that tends to be one of the biggest problems that I see students having is not understanding what is the system and then what is the surroundings, what are the things that are around it. So if we look at this example here, we can see that the system in itself is the part that is the inside. The system is the red and white molecules that we have here. And that is the system. That's everything that's going to be taking place in the reaction. The energy can be leave the system due to work and some of those things, but we'll worry about some of those later. But what the surroundings is everything on the outside of this, everything on the outside, basically. You could do this the same thing with like a car. The system is everything that's inside the car, and then the surroundings is everything on the outside of that. And we need to kind of maintain that, and that is part of the beginning of understanding of system and surroundings. The one thing that students tend to have some difficulty with is understanding that the surroundings can influence the system, and then the system can also influence the surroundings. So we have to be very mindful of what is happening to what, and really specifically sometimes when it comes into the lab of what are we measuring? Are we measuring the surroundings, or are we measuring the system? And so that's going to be the real trick as we move forward. Some definitional stuff, some understanding of some basic physics. First off, we will need to understand what energy is, and is anything that is used to move an object over some distance. A lot of times when in my regular, on my higher end, on my high school physics class, we will talk about work, but I will usually label it and spell it even so that, and as verk, so that we know the separation. Because a lot of times if we said just regular, work that we have, we would think about going to our jobs. And so by calling it verk, we understand that it's something different. So it's just kind of a way to understand that part of it. Now, verk is a force over a distance. There is a further example of that. We will cover that more in regular physics. There's some trigonomic function that is there. We're not going to worry about it, so don't worry about how that looks at. Is that that is what we're going to be measuring. Is sometimes is going to be the verk, and sometimes it might be a distance, but it also is a force over that distance. And so we'll look at some of those where we get some of that. And so what do we mean by energy? And there's a much more depth talk about the whole work energy theorem, as some physics teachers will look at. Energy is the ability to do work, and so you need to have energy to do work or to transfer heat. This is how your refrigerator works. Your refrigerator requires energy to transfer heat away or cold air in, depending on how you want to look at it, and that's how that works. To heat up your stove, there you have to have a transfer of heat, and that is there's energy that is stored within the bonds of like the methane molecule, and that if you look at the methane molecule, the bonds that hold the H's there are have a certain amount of energy to them. And when we break them up in the form of a combustion reaction, that gives off energy, and that's a lot of energy. That energy is released, which allows work to be done. And that's what we're going to get into, is actually how much energy is in those bonds. And so we're going to look at some of that. And it's usually we can use temperature to determine some of these things. It's not the best determining factor, but we can use temperature, and that's because temperature is defined as the average kinetic energy of the system. And so by taking the temperature, we're able to make some other calculations to actually determine how much energy is there. Temperature and energy are not directly related. They're sideways related, kind of almost like on a parallel. So I mentioned kinetic energy on the previous slide, and that comes with the energy, and kinetic energy is equal to 1/2 mass times velocity squared. This is a calculation that you will definitely want to have. I have seen the energy or kinetic energy part, the beginning part, I've seen that also as KE, right? I've also seen it as a number of different variables. I think it's just a time for physics to actually figure out, like, okay, what is the thing that we're going to use, and then just kind of use it forever and always, instead of everybody and every resource using different ones. But we have the kinetic energy is equal to 1/2, and that is our mass, usually in kilograms, and then your velocity, and that is usually in meters per second as well. And so you would need to do some calculations with that to determine the amount of kinetic energy. And kinetic energy is the energy of motion. You can think about it, if some of you have talked about in your career papers about going into kinesiology, the study of movement, how the body moves. And that's because it's kinetic, it's moving. So kinetic energy is the energy of movement. Well, if an object isn't moving, it has potential energy. In physics, we will talk about potential energy usually dealing with gravity, but because we're in chemistry, we're going to talk about the electrostatic potential energy that objects have based on their proximity to each other. And some of that comes from the type of molecule or the charge that the molecule has. And so that changes. And so what it as, and it's a little more of an electrostatic potential energy. That means charges, electrostatic meaning the charge. And that's what you're looking at with these Q values, are the charges. And that the D value down here is your distance, how far apart. And K is a constant, usually will be given to you, or something that you might need to calculate. And given those bits of information, you should be able to calculate the amount of potential energy, the amount of energy that they could have if they were there. So potential energy does lead usually to kinetic energy, depending on when the object is moving. And these are just potentially how much energy is stored. In physics, that change or transfer is something that we'll talk about later, and that is that transfer between potential energy and the other. And we also have other potential energies, like I talked about, storing the energy within the bonds, is loosely related with this, although some of them are molecular bonds, and so they're not exactly always the same. They just require other things, and so we have some of that there. Now, this energy, as we can see, can be transferred. Energy flows from warmer objects to cooler objects. So when your dad during the winter time says, who left the door open? You're letting all the cold air in, is actually a false statement, in that you're actually letting the warm air out, which gives you the feel or the perception that it's actually getting colder. But that's just how that works. And it's that information, that this understanding that heat flows from a warmer object to cooler object, is something that we're definitely going to be utilizing in the lab, because we're going to be having to heat something up and then put it in another container, and then we will determine that where that energy is flowing to, because we'll know the beginning temperatures. And so that energy flow, or the heat flowing from warmer objects to cooler objects, and that's that transferring of heat. This will again, this is just a little bit of an introduction to what energy is, some of the terminology that we're going to use, and understanding what things are going on with this. Some of the other understandings of what is a system and what is the surroundings. In the picture that we have here, we can say that the surroundings could be everything outside of this glass here, where the system is the water that's inside. And therefore, the surroundings are doing work on the system. Therefore, the energy is going up, and that's why it's starting to boil. We could look at them as two different systems as well, and that the natural gas down below could be its own system as well. But then we start we complicate things very much so. But in a simplistic view, the surroundings and the system is what's inside the bowl. And a lot of times I like to say, it's inside the beaker, it's inside the test tube, it's inside something, it's contained within something, and therefore the surroundings is everything on the outside. And that's where that understanding and that envisioning of what's going on is so important as we continue forward with this.